Okay, so we're going to look at a problem of uniform circular motion where we have a ball on a string. Let's imagine there's a string hanging with a giant bowling ball in the middle of your classroom, and it's hanging straight down. The string has a length of 4.5 meters. I pull the ball back and I let go of it and let it swing like a pendulum. Okay, so it's going to swing down and back. Now, at the very bottom of the swing, at the very bottom, I know that that ball is going at 5.5 meters per second. Because it's at the very bottom of this circular swing, it's heading in that horizontal, so that's where I show my arrow of the velocity, and I'm going to turn that velocity by that string. The ball has a weight of 100 newtons, which gives me a mass of 10.2 kilograms. What is the tension in the string at the when the ball is at the very bottom? What's that tension T? All right, so we're interested in tension, we're interested in forces, and those forces are acting on the ball. So let's look at our object, the ball, and let's look at the interactions. Well, we know we have the force of gravity. That's between the ball and the earth. And the other interaction, well, the string is in contact with the ball. It's interacting with the ball. So we also have the force of the string. Remember, we call that a tension. And that is between the ball and the string. There's not really anything else going on. There's no other interactions happening. So we'll take those interactions and we'll develop them into our free body diagram. Here's our ball. We know we have the force of gravity, which of course is equal to the weight, which is mg, and that points down, earth vertical. And then we have the string, and at the very, very bottom, what direction is the string interacting with the ball? Well, it's holding it up, pulling it up. So we have the tension in the string. All right, those are our two forces. Now we want to think about the separating those forces into vertical and horizontal components. And when we do that, we think about the direction of the acceleration. Is there an acceleration, and what is that direction so that I can align my coordinate system with the acceleration? Well, the object's moving in a circle, so it's changing its velocity, it's changing its direction, so there has to be an acceleration. And what is the direction of that acceleration? Well, at the very bottom of my swing, the acceleration to move an object in a circle, the centripetal acceleration, is in the direction towards the center. So in this case, the acceleration is in that direction. It's along a vertical axis, so we don't need to rotate our coordinate system. It's along one of our orthogonal, our normal coordinate systems. All right, so let's separate into our normal horizontal and verticals. Well, I don't really have any horizontal, so we're just going to look at the vertical forces. 1 and 2. My vertical force for force 1, my force of gravity, well, that's minus mg. It's pointing in the downward direction, has magnitude of mg. It is given the weight, so we'll put both of those in. And my tension is pointing in the upward direction, so we're going to call that just T. Right? Moving through our analysis, we know that the forces acting, the sum of the forces acting in any one direction provide that direction's the acceleration of that object in that direction. So we know that the sum of the forces, the net force, is equal to mass times acceleration vertically. And we said that that object is moving in a circle, so that vertical acceleration is our centripetal acceleration. So we're going to sum these forces. Minus W plus T is equal to our mass times our centripetal acceleration. And we want to remind ourselves that the magnitude of the centripetal acceleration is the speed squared over the radius. And the direction, which we have to be explicit about, is towards the center. Why do we have to be explicit? Well, we're about to input something that doesn't have direction, a speed, so we have to be very clear about the direction of that centripetal acceleration. So, rewriting that, I have minus the weight plus the tension equals m, our magnitude of v squared, or speed squared, but v squared over r. And what is the direction? Well, we identified that direction as being positive. So I have a positive v squared over r. And this is not a plus, but a direction. So I'm gonna erase that. Okay, so now let's solve for the tension. The tension then must be m times the speed squared over the radius plus the weight. Let's move that up here. And our tension is equal to our mass, 10.2, our speed, 5.5 squared, our radius of 4.5, plus our weight of 100. So the tension in that string is 10.5 times 5.5 times 5.5 divided by 4.5 plus 100. The tension is 170.6 newtons. Now, does that make sense? Well, if you're swinging your lanyards on a key round and around, how does it feel when they get to the bottom? You're kind of pulling them versus if they're just hanging there. More force is required to get them to swing in that circle than just to hold them steady. There's our difference. More force is required in the upward direction than the downward direction to change the direction than just to hold it steady. So it's reasonable that our tension is higher than our weight. Both, remember, contribute to that circular motion because both are in the direction of that circular motion. All right? Good job.